Hi, I'm Stefan Lenz, Application Scientist at Chemical Computing Group. In today's session, I'll demonstrate how to calculate protein properties related to stability, solubility, and viscosity. We'll compute the properties on a static structure and on an ensemble of structures to enhance the accuracy by considering both changing pH and conformational dynamics. I'll start by loading in a structure of hen-egg lysozyme. And today we'll focus on the degradation liabilities of solvent-exposed residues in this model system. But it's important to note that our workflow could be used to improve the developability of antibodies or peptides. Since I've already prepared the structure with Quick Prep, I'll jump right into calculating the protein properties. The protein properties panel has two tabs: the property calculation tab, where we can set up the environment, and select the properties to calculate, and the property viewer tab, where we can view the properties once we've calculated them. Today, I'll calculate the properties on the structure that we have loaded into Mo, though I could also calculate them for multiple structures stored in a database. I'll leave sample unchecked and compute the properties on a static structure for now, and I'll also keep the pH, temperature, and salt concentration at their defaults. By default, we've pre-selected 28 protein descriptors out of a total of 112, and among these are commonly used per residue and molecular descriptors for various properties, including mass, charge, and shape. We can also add in custom descriptors to this list. I'll select two additional descriptors to help me assess the solvent accessibility of backbone nitrogen atoms. Next, I'll calculate the properties. Once the calculation is completed, the tab will automatically switch to the property viewer. And here we have the calculated per residue and molecular descriptors, including hydrophobic patch areas, PIs, residue pKa's, and residue charge. Today, I'm interested in evaluating the degradation liabilities. As an example, I'll focus on two asparagines, asparagine 93 and asparagine 103, that are part of deamidation motifs. And first, I'll examine the solvent exposure of both of these residues. I can see that both residues are solvent exposed, with asparagine 93 being about 40% exposed and asparagine 103 being about 60% exposed. Next, I'll examine the solvent exposure of the backbone nitrogens of the residues following both asparagines, since if exposed, these nitrogens can initiate deamidation of the side chains. For this, I'll toggle on the residue table to get a summary of the computed per residue properties, and I'll sort by residue to view my asparagines together. I see that the backbone amide following asparagine 93 is not exposed, but the amide following asparagine 103 is exposed with a value of around 5 angstroms squared. And so this indicates that asparagine 103 could be prone to deamidation. Now, all of the analysis I've done up to this point has been based on a single static structure. Since protein properties are sensitive to both conformation and pH, I'll compute the properties on an ensemble of structures sampled over a pH range. These ensemble average properties correlate better with experiment because they account for protein flexibility and protonation state changes. But before I do that, I'm going to save my results to a database. I'll call it prosampstatic.mdb. And this database will have the structure that we calculated the protein properties on, along with all of the different protein properties that we selected. I'll close the database for now. To calculate the ensemble average properties, I'll navigate back to the property calculation tab, and this time I'll enable sample. I'll also set the pH range to be between 3.4 and 11.4. And we'll sample 50 conformations per unit of pH for a total of 400 conformations. So here we're simultaneously sampling both conformational and protonation space using low-mode MD and Protonate 3D to improve the accuracy of our computed protein properties. This will take more time than the static prediction, so for that reason, I'll load in pre-calculated results. Here's a good opportunity to mention that when we do save our protein properties, two databases are created: a summary database with the ensemble average properties, and another database containing the properties for each individual conformation. I'll load in the summary database, and I'll open up the protein properties panel. So here I see the ensemble average properties on the left and the plot area on the right. And the plot area allows us to visualize how properties change with pH. For example, if I'm interested in Ensemble net charge, I can select it. And I can see that the isoelectronic point is around 11. If I'm interested in predicting properties at other different, perhaps lower pHs, I can click into the plot, noting that all of the properties I have on the left are automatically being updated. I can also specify an exact pH, for example, by clicking into the pH box, and this time I'll specify 7.4 and return to our default. Okay, so let's get back to our original example and look at the Ensemble average properties for both asparagine 93 and asparagine 103. So I'll toggle on the residue table again, and this time I'll just navigate to the two asparagines of interest. I can see that as before, both are relatively solvent exposed, with 93 being 40% and asparagine 103 being about 50%. And if I look at the exposure of the backbone amides following both of these asparagines, I can see that the one following 93 remains relatively unexposed, but it's quite exposed for asparagine 103, about 2.5 angstroms squared. This is supported by this other descriptor that we calculated, this fractional amide N, which measures the fraction of structures with an exposed backbone nitrogen. For asparagine 93, only about 4% of these structures are exposed, but for asparagine 103, it's about 80%. Let's take a look at the structure. So I have both asparagines selected. I'll also select the residue following both asparagines, and I'll visualize them in the main mo window. Take a moment to clean up the visualization. And we'll focus in on cysteine 94 and asparagine 93 to start. I can see that if we look at the backbone amide for cysteine 94, it's part of an alpha helix. It could perhaps hydrogen bond with a nearby carbonyl, so it doesn't appear exposed and it's unlikely to react with the asparagine 93 side chain. In contrast, if I focus in on asparagine 103 and glycine 104, I can see that the backbone amide of glycine 104 isn't part of a secondary structure motif. It doesn't seem to be hydrogen bonding with anything, and it appears relatively solvent exposed. So it could potentially initiate deamidation. So our structural analysis aligns with the Ensemble average properties that we computed a moment ago. And that brings us to the end of today's session. Today, we calculated the pH-dependent protein properties for both a static structure and on an ensemble of structures, and we use these properties to help us evaluate the degradation liabilities of two solvent-exposed residues. So I hope you've learned a lot, and if you have any questions, please do reach out to me at support@chemcomp.com.